So we just talked about the relative strength of each acid and base compared to water. Now, what happens though when you don't put any acid or base as a solute in water? What happens if you just have liquid water around? Remember that water could act as an acid and as a base. We call this amphiprotic nature of water. Right? And so if we just have a container of pure water, it actually does this reaction here where one of the water acts as an acid and then another water acts as a base. So one donates a proton, the one that gives away proton then become OH minus after it gives away the proton, so that's the conjugate base. And then the base here accepts a proton and it becomes the hydronium ion. So the reaction looks like this. This is what we refer to as the auto-ionization process. Now, why auto-ionization? Because it does it on its own, right? Sometimes also called the auto-association reaction, and this is because if you're thinking about it from the Arrhenius equation perspective, you can write it as this, H plus and OH minus, but it's the same reaction. Okay, so just keep in mind that hydronium and proton represent the same species. If you want to write the K for this reaction, remember that the concentration of liquid is a constant, so it doesn't factor into the K expression. So the K expression is just going to be concentration of H plus at equilibrium times the concentration of OH minus at equilibrium. At the bottom here, we see it written as the hydronium times hydroxide concentration, but it's the same idea. Now, this number can actually be measured at 25 degrees Celsius. The value of Kw, called Kw for water, it's 10 to the minus 14. This is a really useful relationship because for any species containing H plus and OH minus in water, it has to satisfy this equilibrium, meaning that at equilibrium, the product of H plus times OH minus always has to equal 10 to the minus 14 for any reaction at 25 Celsius. I emphasize the temperature here because if you recall our discussion in equilibrium, K value can change as a function of temperature. So if I increase temperature or decrease temperature, that Kw value will change. And if the Kw change, then of course that will affect our calculation as well. Okay. In fact, we know that this process is endothermic. So based on our Le Chatelier principle analysis, when you increase temperature, the K value would actually increase. So for example, here the Kw is actually 5.6 times 10 to the minus 13 at 100 degrees Celsius, which is about 50 times larger than what it is at 25 degrees Celsius. If you're not told anything else, you can assume that you're dealing with 25 Celsius, you can use 10 to the minus 14. One of the beauty of this relationship between hydronium and hydroxide and water, or any water-based solution, is you can calculate one once you know the other one. So for example, we were told here that OH minus is 0.0025 in this problem. What's the H plus? All we know is H plus times OH minus has to equal 10 to the minus 14. And so knowing OH minus allows us to calculate H plus, which is just 10 to the minus 14 divided by 0.0025, which ends up giving us 4 times 10 to the minus 12 molar. Okay, again, this only works if the solutes are in the presence of water, right? So once we know how to calculate that, the next thing we need to know is, does that mean that its solution is acidic or is it basic? We care about this because the kind of reactions that we can do, the type of chemistry that happen, depends on whether you have an excess of H plus or excess of OH minus. A lot of biological examples you can think of that would not work if you have too much H plus or too much OH minus. For example, in blood, the acidity has to be a certain level. If it's too acidic, then certain things like absorption of oxygen and all these other biological functions will not occur at the same efficiency. So it's really important to know how acidic something is, the solution is. And so we're going to talk about measure of acidity here. And there's two measures. The main measure is this one right here, which is comparing the relative concentration of H plus and OH minus. And simply what we say here is that if you have more H plus than OH minus, then that solution is acidic. If you have less H plus and OH minus, it's basic. If you have equal number, then we call it neutral. So that's really the main way we determine whether something is acidic or basic. So here's an example. If the OH minus is this, is the solution acidic, basic, or neutral? Well, we can first calculate the H plus. So remember that H plus is just going to be Kw over OH minus. Once we calculate that, we find that H plus is 5.5 times 10 to the minus 7. 10 to the minus 7 is bigger than 10 to the minus 8. And so therefore H plus is bigger than OH minus. So the solution is acidic. Okay.
This calculation takes a few steps.
So we want something that's quick that we can just look at and determine whether the solution is acidic or basic or neutral. So we use this scale called the pH scale. Simply what this means is that instead of looking at two numbers like what we just did, H plus, OH minus, we're just looking at H plus now. And this is specifically at 25 Celsius. So pH itself is just a mathematical operation where you take the negative log of the H plus concentration or the hydronium concentration, okay? And if your H plus is 10 to the minus 7, remember that our Kw earlier is 10 to the minus 14. So H plus, when H plus and OH minus are equal to each other,
we can calculate their concentration using the Kw value.
Kw, which is 10 to the minus 14, should equal x squared, where x represents the concentration of H plus or OH minus since they're equal here. So therefore, x would be 10 to the minus 7. And that's where that 10 to the minus 7 comes about. So if H plus is 10 to the minus 7, pH, which is just the negative log of 10 to the minus 7, is going to be equal to 7. So therefore, we would say a neutral solution is a solution that has a pH equals 7. Now, you can then work out the other two situations. If the H plus is more than 10 to the minus 7, when you do that pH operation, the pH actually will be less than 7. The reason for that is because we have a negative sign here, which gives us an inverse relationship. So an acidic solution will have pH less than 7. Basic solution, on the other hand, would have a pH of greater
than 7.
In practice, when you want to measure pH, you typically just use what we call a pH meter, which looks like one of these two things here. And as you can see, you just put that pH meter in your solution and you get a number. In this case,
10.33,
which tells you it's a basic solution. This one is 7.053, which is just slightly basic. It's a little above neutral. Okay. As I said earlier, Kw changes as a function of temperature, just like any equilibrium constant. Very important to keep in mind that if you're doing your experiment at a temperature different than 25 Celsius, which often happens, say you're studying warm-blooded animals
whose body temperature
is, about 35 degrees, then you're not going to assume that pH equals 7 is neutral. In fact, pH equals 7 might be acidic, it might be basic, it depends on what temperature you're studying. I'll also mention this side note, which is this operator P that we use here for pH. You will see that it's going to be used for other chemical concentration and equilibrium constants as well. The general meaning of that operator P is just negative log. So anytime you do
P of x, it just means to take the negative log of x.
Let's take a look at this problem of calculating pH. It tells you that the H plus ions concentration in a wine bottle at the beginning is 3.2 times 10 to the minus 4. And then after you leave it for a while and then you try to drink it again, the H plus concentration now it's 1 times 10 to the minus 3. And the question is, what is the pH of the wine at two different occasions? And you can see that if we just plug in that formula of negative log of the H plus concentration, here's the beginning, here's the end, and we get these numbers respectively. So the pH has dropped, the wine has become more acidic, and of course that affects, the taste. We had talked about catalysis when we're discussing kinetic. Acids a lot of times are catalysts for certain reactions, so it might be that having more acid catalyze other reactions that make the wine taste even worse than just the change in the pH alone. But for sure, there's at least acidity of the wine as you go from the beginning to the end there.